We want to be able to pick up our collectible game objects when our player game object collides with them. To do this, we need to detect our collisions between the player game object and the pickup game objects. We will need to have these collisions trigger a new behavior, and we will need to test these collisions to make sure we are picking up the correct objects. The pickup objects, the player's sphere, the ground plane, and the walls all have colliders that inform us about collisions. If we didn't test our collisions to find out which objects we've collided with, we could collect the wrong objects. We could collect the floor or the walls. As a matter of fact, if we didn't test our collisions, on the very first frame of the game, we would come in contact with the ground plane, and we would collect the ground plane, and then we would fall into the void of the scene space, and the game would essentially be over. First, we don't need our player to remain inactive, so let's tick the active checkbox and bring back our player. Next, let's select the player controller script and open it for editing. Just a note, we could edit this script regardless of whether the game object is active or not. Inactive. So let's tick the active checkbox and bring back our player. Next, let's select the player controller script and open it for editing. Just a note, we could edit this script regardless of whether the game object is active or not. Now that we have the script open, what code are we going to write? We could write collider, and then search the documentation using the hotkey combination. But there is a different way that we could do this as well. Let's return to Unity and look at the details of our player game object. What we are interested in here is the sphere collider component. In the header of each component on the left is the component's turn-down arrow, the icon, the enabled checkbox if it's available, and the type of the component. On the right is the context-sensitive gear gizmo, and an icon of a little book with a question mark. Now this is what we need. This is the quick link to the component reference. If we select this icon, we are taken not to the scripting reference, but to the component reference. We would read this document to find out more about how to use this component in the context of the editor. We, however, want to find out how to script to this component's class. To do this, we simply switch to scripting, and we are taken to the scripting reference for the sphere collider. We want to detect and test our collisions. For this project, we are going to use onTriggerEnter. Just imagine if we were, say, a daring plumber, and we jumped up to collect a perfect arc of coins, and bounced off the very first one as we collected it and fell back to the ground. Not very elegant. This code will give us the ability to detect the contact between our player game object and our pickup game objects without actually creating a physical collision. The code example, however, is not exactly what we're looking for. But that's okay, we can change that. First, let's copy the code. And then let's return to our scripting application. Now that we're back in scripting, let's paste the code. As we have copied this code from a web page, let's correct the indents. In this case, I'm going to make sure the indents are tabs and that all of the tabs are correctly aligned. Next, let's look at this code. We are using the function onTriggerEnter. OnTriggerEnter will be called by Unity when our player game object first touches a trigger collider. We are given as an argument a reference to the trigger collider that we have touched. This is the collider called Other. This reference gives us a way to get a hold of the colliders that we touch. With this code, when we touch another trigger collider, we will destroy the game object that the trigger collider is attached to through the reference other.gameObject. By destroying that game object, the game object, all of its components, and all of its children and their components are removed from the scene. For the sake of example in this assignment, we won't destroy the other game object, we will deactivate it, just like we deactivated the player object when we were creating our pickup objects. First, let's remove the destroy other game object code from the function. But let's paste it down below our script as a palette to work with. How will we deactivate our pickup objects? Well, what clues do we have? We can address the other collider's game object through other.gameObject. We can see this here in the sample code. And we want to test the other game object, and if it's a pickup object, we want to deactivate that game object. So let's look up game object with our hotkey combination and see what we can find. Now we have the page on game object. There are a few important items here that we want. They are tag. Tag allows us to identify a game object by comparing the tag value to a string. And setActive. This is how we activate or deactivate a game object through code. The last item we need to know about is compare tag. Compare tag allows us to efficiently compare the tag of any game object to a string value. Let's open up these three items, each in their own tab. Tag allows us to identify a game object by a tag value. We must declare our tags in the Tags and Layers panel before using them. It is possible to test a tag against a string value directly with code like if gameObject.tag is the same as some string value. But there is a more efficient built-in way to do this, and that is compare tag. With compare tag, we can efficiently compare the tag of any game object with a string value. Let's copy the sample code and paste it into our working palette. Now, game object setActive. This is how we activate or deactivate a game object. This is the code equivalent of clicking the active checkbox next to the name field in the inspector. In our case, just like the code snippet, we will call GameObject setActive false to deactivate our pickup game objects. Let's copy this code and, returning to our script editor, paste it into our palette as well. I feel we have enough pieces to write our code. So let's write if other.gameObject.compareTag with the string value of pickup. And we will have to declare this tag in Unity later. Other.gameObject.setActive false. Now this code will be called every time we touch a trigger collider. We are given a reference to the collider we touch. We test its tag, and if the tag is the same as the string value pickup, we will take the other game object and we will call setActive false, which will deactivate that game object. Now, we don't need this code we've been saving anymore, and keeping it will only confuse the compiler, so we can delete it. Let's save this script and return to Unity and check for errors. The first thing we need to do is set up the tag value for the pickup objects. Select the prefab asset for the pickup object. When we look at the tag list, we don't see any tag called pickup, so we need to add one. Select Add Tag. And this brings up the Tags and Layers panel. Here we can customize tags and layers pickup, so we need to add one. Select Add Tag. And this brings up the Tags and Layers panel. Here we can customize tags and layers. Note that this tags list is empty. To create a new custom tag, select the plus button to add a new row to the tags list. In the new empty element, in our case tag 0, type pickup. And this is case sensitive and needs to be exactly the same string that we have in our script. If in doubt, we can copy and paste this string to get the exact value. When we look back at the prefab asset, note that the asset is still untagged. By selecting Add Tag, we changed our focus from the prefab asset to the Tag Manager. And in the Tag Manager, we created our tag. Now we need to apply that tag to the prefab asset. Select the Tag drop-down again, and see how we now have Pickup in the list. Select this tag from the list, and the asset is now tagged Pickup. And, with the power of prefabs, all of the instances are now tagged Pickup as well. Now let's test our game. Save the scene and enter play mode. Okay. Our tag is set to Pickup, but we are still bouncing off the Pickup cubes just like we are bouncing off the walls. So let's exit play mode. Before we discuss why we are bouncing off the Pickup cubes rather than picking them up, we need to have a brief discussion about Unity's physics system. I'm going to enter play mode for this discussion. Let's look at one of our cubes and our player. As an aside, we can select 2 or more game objects at the same time and inspect them all. We do this by holding down the Command key on the Mac or the Control key on the PC and selecting the game objects. When we select multiple game objects, note how the inspector changes to show the common components and property values of the selected game objects. The inspector also allows for multi-object editing. Using multi-object editing, I'm going to disable the mesh renderer on both the player sphere and the selected cube with a single click. This leaves us with the 2 green outlines of the collider volumes for these 2 objects. How do collisions work in Unity's physics engine? The physics engine does not allow 2 collider volumes to overlap. When the physics engine detects that any 2 or more colliders will overlap that frame, the physics engine will look at the objects and analyze their speed and rotation and shape, and calculate a collision. One of the major factors in this calculation is whether the colliders are static or dynamic. Static colliders are usually non-moving parts of your scene, like the walls, the floor, or the fountain in the courtyard. Dynamic colliders are things that move, like the player's sphere or a car. When calculating a collision, the static geometry will not be affected by the collision, but the dynamic objects will be. In our case, the player's sphere is dynamic or moving geometry, and it is bouncing off the static geometry of the cubes, just as it bounces off the static geometry of the walls. The physics engine can, however, allow the penetration or overlap of collider volumes. When it does this, the physics engine still calculates the collider volumes and keeps track of the collider overlap. But it doesn't physically act on the overlapping objects. It doesn't cause a collision. We do this by making our colliders into triggers or trigger colliders. When we make our colliders into a trigger or trigger collider, we can detect the contact with that trigger through the on-trigger event messages. When a collider is a trigger, you can do clever things like place a trigger in the middle of a doorway in, say, an adventure game. And when the player enters the trigger, the minimap updates and a message plays, "You have discovered this room." Or every time your player walks around that corner, spiders drop from the ceiling, because the player has walked through a trigger. For more information on collision and on-trigger messages, see the lessons linked below. We are using on-trigger enter in our code rather than on-collision enter, so we need to change our collider volumes into trigger volumes. To do this, we must be out of play mode. Let's select the prefab asset and look at the box collider component. Here we select is trigger, and again, the power of prefabs, all of our pickup objects are now using trigger colliders. Let's save our scene, enter play mode, and test. And as our player enters the trigger, we pick up the objects. Excellent. Let's exit play mode. Everything looks great. We only have one issue. We have made one small mistake, and this is related to how Unity optimizes its physics. As a performance optimization, Unity calculates all the volumes of all the static colliders in a scene and holds this information in a cache. This makes sense as static colliders shouldn't move, and this saves recalculating this information every frame. Where we have made our mistake is by rotating our cubes. Anytime we move, rotate, or scale a static collider, Unity will recalculate all the static colliders again and update the static collider cache. To recalculate the cache takes resources. We can move, rotate, or scale dynamic colliders as often as we want, and Unity won't recache any collider volumes. Unity expects us to move colliders. We simply need to indicate to Unity which colliders are dynamic before we move them. We do this by using the rigid body component. Any game object with a collider and a rigid body is considered dynamic. Any game object with a collider attached but no physics rigid body is expected to be static. Currently, our pickup game objects have a box collider, but no rigid body, so Unity is recalculating our static collider cache every frame. The solution is to add a rigid body to the pickup objects. This will move the cubes from being static colliders to being dynamic colliders. Let's save and play. And our cubes fall through the floor. Gravity pulls them down, and as they are triggers, they don't collide with the floor. Let's exit play mode. If we look at the rigid body component, we could simply disable Use Gravity, which would prevent the cubes from being pulled downwards. This is only a partial solution, however. If we did this, even though our cubes would not respond to gravity, they would still respond to physics forces. There is a better solution, and that is to select Is Kinematic. When we do this, we set this rigid body component to be a kinematic rigid body. A kinematic rigid body will not react to physics forces, and it can be animated and moved by its transform. This is great for everything from objects with colliders, like elevators and moving platforms, to objects with triggers, like our collectibles, that need to be animated or moved by their transform. For more information on the rigid body and Is Kinematic, see the lessons linked below. Let's save our scene and enter play mode to test. Now our behavior is identical and performant. So, static colliders shouldn't move, like walls and floors. Dynamic colliders can move and have a rigid body attached. Standard rigid bodies are moved using physics forces. Kinematic rigid bodies are moved using their transform. In the next assignment, we will count our collectible objects and make a simple UI to display our score and messages. Counting, displaying text, and ending the game. We need a tool to store the value of our counted collectibles, and another tool to add to that value as we collect and count them. Let's add this tool to our player controller script. Select the player game object and open the player controller script for editing. Let's add a private variable to hold our count, This will be an int, as our count will be a whole number. We won't be collecting partial objects. And let's call it count. So in our game, we will first start with a count of 0. Then we will need to increment our count value by 1 when we pick up a new object. First, we need to set our count value to 0. As this variable is private, we don't have any access to it in the inspector. This variable is only available for use within this script, and as such we will need to set its starting value here in the script. There are several ways we can set the starting value of count, but in this assignment we will do it in the start function. In start, set our count to be equal to 0. Next, we need to add to count when we pick up our collectible game objects. We will pick up our objects in onTriggerEnter if the other game object has the tag pickup. So this is where we add our counting code. After setting the other game object's active state to false, we add our new value of count is equal to our old value of count plus 1. There are other ways to add, count up, or increment a value when coding for Unity, but this one is very easy to understand, and this is the one that we're going to use in this assignment. Save this script and return to Unity. Now we can store and increment our count, but we have no way of displaying it. It would also be good to display a message when the game is over. To display text in this assignment, we will be using Unity's UI toolset to display our text and values. First, let's create a new UI text element from the hierarchy's Create menu. Let's look at what we've added to the hierarchy. We seem to have gotten more than. First, let's create a new UI text element from the hierarchy's Create menu. Let's look at what we've added to the hierarchy. We seem to have gotten more than we bargained for. We don't just have a UI text element, but we've also created a parent canvas element and an event systems game object. These are all required by the UI toolset. The single most important thing to know about these additional items is that all UI elements must be the child of a canvas to behave correctly. For more information on the UI tools, including the canvas and the event system, please see the information linked below. Rename the text element CountText. So let's customize this element a bit. The default text is a bit dark. Let's make the text color white, so it's easier to see. The size and alignment are good. And let's add some placeholder text, count text. We want our text to display in the upper left of the screen when the game is playing. We can see. Let's make the text color white, so it's easier to see. The size and alignment are good. And let's add some placeholder text, count text. We want our text to display in the upper left of the screen when the game is playing. We can see that the UI text is currently displaying in the center of the screen in the game view. This is because the text element is anchored to the center of its parent, which is, in this case, the canvas. It is worth noting that the transform component on UI elements is different from the other game objects in Unity. For UI elements, the standard transform has been replaced with the rect transform, which takes into account many specialized features necessary for a versatile UI system, including anchoring and positioning. For more information on the rect transform, please see the information linked below. One of the easiest ways to move the count text element into the upper left is to anchor it to the upper left corner of the canvas, rather than to its center. To do this, open the Anchors and Presets menu by clicking on the button displaying the current anchor preset. When we re-anchor this text element, we also want to set the pivot and the position based on the new anchor. So we will hold down both the Shift and the Alt keys, and then select the upper left corner button. That's done it, it's up in the corner. But now it looks budged up against the corner of the game view. Let's give it some space between the text and the edges of the screen. as we are anchored to the upper left corner of the canvas, and we've set our pivot to the upper left corner as well. The easiest way to give the text a little breathing room is to change the rect transform's pos x and pos y values. 10 and minus 10 seems about right, with some room around it, yet it's still up and out of the way. So let's wire up the UI text element to display our count value. Start by opening the player controller script for editing. Before we can code anything related to any UI elements, we need to tell our script more about them. The details about the UI toolset are held in what's called the corner of the game view. Let's give it some space between the text and the edges of the screen. As we are anchored to the upper left corner of the canvas, and we've set our pivot to the upper left corner as well, the easiest way to give the text a little breathing room is to change the rect transform's pos x and pos y values. 10 and minus 10 seems about right, with some room around it, yet it's still up and out of the way. Room, screen, corner button. We also want to set the pivot and the position based on the new anchor. So we will hold down both the Shift and the Alt keys, and then select the upper left corner button. That's done it, it's up in the corner. But now it looks budged up against the corner of the game view. Let's give it some space between the text and the edges of the screen. Up in the corner, text element into the upper left is to anchor it to the upper left corner of the canvas rather than to its center. To do this, open the Anchors and Presets menu by clicking on the button displaying the current anchor preset. When we re-anchor this text element, we also want to set the pivot and the position based on the new anchor. So we will hold down both the Shift and the Alt keys, and then select the upper left corner button. That's done it, it's up in the corner. But now it looks budged up against the corner of the game view. Let's give it some space between the text and the edges of the screen. As we are anchored to the upper left corner of the canvas, and we've set our pivot to the upper left corner as well, the easiest way to give the text a little breathing room is to change the rect transform's pos x and pos y values. 10 and minus 10 seems about right, with some room around it, yet it's still up and out of the way. So let's wire up the UI text element to display our count value. Start by opening the player controller script for editing. Before we can code anything related to any UI elements, we need to tell our script more about them. The details about the UI toolset are held in what's called a namespace. We need to use this namespace, just as we are using Unity Engine and System Collections. So, to do this, at the top of our script write using unityengine.ui. With this in place, we can now write our code. First, create a new public text variable called countText to hold a reference to the UI text component on our UI text game object. We need to set the starting value of the UI text's text property. We can do this in Start as well. Write countText.text equals the string value of count :space plus count to string. And we need the parentheses. Now this line of code must be written after the line setting our count value. Count must have some value for us to set the text with. Now we also need to update this text property every time we pick up a new collectible. So in onTriggerEnter, after we increment our count value, let's write again countText.text equals count :space plus count to string. We've now written the same line of code twice in the same script. This is generally bad form. One way to make this a little more elegant is to create a function that does the work in one place, and we simply call this function every time we need it. Let's create a new function with void set count text, and then an empty set of parentheses and brackets. Now let's move one instance of this line of code into the function by cutting and pasting it. And in its place, let's put a line of code simply calling the function. Finally, let's replace the other line with the function call as well. Excellent. Save and swap back to Unity. Now we can see our player controller script has a new text property. We can associate a reference to our count text simply by dragging and dropping the count text game object into the slot. Unity will find the text component on the game object and correctly associate the reference. Now let's save, enter play mode, and test. Aha! Not only do we collect these objects, but we count them now. Let's exit play mode. We need to display a message, text, simply by dragging. Finally, let's replace the other line with the function call as well. Excellent. Save and swap back to Unity. Now we can see our player controller script has a new text property. We can associate a reference to our count text simply by dragging and dropping the count text game object into the slot. Unity will find the text component on the game object and correctly associate the reference. Now let's save, enter play mode, and test. Aha! Not only do we collect these objects, but we count them now. Let's exit play mode. We need to display a message when we have collected all of the cubes. To do this, we will need another UI text element. Again, using the Hierarchies Create menu, make a new UI text element and rename it WinText. Note how this new UI text element is automatically added to our canvas. Again, as before, let's customize the values on the component. Let's color the text white so it is easier to see. Let's make the text a little larger. Let's try about 24. Lastly, let's adjust the alignment to center and middle. And again, let's add placeholder text. WinText. We want this text to display in the center of the game screen, but up a little so it doesn't cover the player game object. To do this, simply adjust the rect transform's pos y value, as by default, this UI text element is anchored to the center of the canvas. A value of about 75 feels good. Save the scene and swap back to the scripting editor. We need to add a reference to this UI text element. Create a new public text variable and call it WinText. Now, let's set the starting value for the UI text's text property. This is set to an empty string, or 2 double quote marks with no content. This text property will start empty. Then in the setCountText function, let's write if count is greater than or equal to 12, which is the total number of objects we have in the game to collect, then our winText.text equals you win. Save this script and return to Unity. Again, on our player controller has a new UI text property. We can associate the component, again by dragging the WinText game object into the slot. Save the scene and play. So we're picking up our game objects. We're counting our collectibles. And we win! And as we can see, when we have collected 12 objects, we display the "You win" text. In the next and last assignment of this series, we will build the game and deploy it using a standalone player. Now that we've finished our game, we need to present it to our players. One of the greatest things about Unity is that once we have created our game, we can deploy it to many of the current platforms. For more detailed information on building and build targets, please see the lesson linked below. Before we build our game, we should save our scene. To build our game, we must first open the Build Settings window. We can do this by selecting File, Build Settings, or by using the key combination of Shift plus Command or Control plus B. This brings up the Build Settings window. Our current build target is indicated by the Unity logo. The blue highlight indicates our focus and shows us, on the right-hand side, the build options for the currently selected platform. We want to build a standalone application. This is our current build target: PC, Mac, and Linux standalone. We do not need to change our build target. If we did want to change our build target, we can select the desired platform from the list and click the Switch Platforms button at the bottom of the window. Let's now return our build target to the standalone player. Once we have selected our new build target, we need to add the scenes we want to build to the Build Settings window. We can add the current scene by clicking the Add Current button, or we can drag and drop any scene from our project view into the field at the top of the Build Settings window. It's worth noting that we don't need to include every scene in our project. We only need to include the scenes we want in our game. It is also possible to perform a build with no scenes in the Build Settings window. If we do this, Unity will simply build our game using the current scene we have open for editing. Now we are ready to build our game. Let's return to the Build Settings window and click the Build button. This will bring up a dialog box asking us to choose a build location. I like to associate my build location with my project, so I will create a new folder inside my project called Builds. This folder must be placed only on the root of our project alongside the assets and library folders. With the build folder selected, let's name the build. And then click Save. Unity will now build the application and save it to our Builds folder. When building for the Mac, Unity builds a .app bundle, which contains all of the relevant data and files. When building for Windows, Unity builds a .exe file and a data folder which contains all of the necessary resources. To run the game, simply run the executable application. And now we are running our game. And we win! So, in these assignments, we have learned how to create new game objects, how to position them in the scene, add new components to them, write our own custom behaviors for them using simple scripting. We've seen how to use lights, cameras, colliders, triggers, rigid bodies. We can collect and count objects. Though this is a very simple example, it covers a large set of basic subjects important to understanding how to use Unity. For continued learning about Unity, check the Learn site for more lessons, assignments, and projects.